Okay, I think maybe everything is in order on my end now, so we can get started. And first off, in case you didn't see in Discord, um, yeah, I was behind in getting the lesson videos dealt with last week, and then got kind of, yeah, I don't know what happened, honestly. I just sort of didn't manage to get them posted and didn't have time to post them at the end of the week. So the lesson video for last week is still not up, but I will try to get both the lesson video from last week and the one from today up sometime tomorrow. So as a result, I think it's fair to give you a few extra days for the exercise number 5, because at least the exercise 5 tips notebook that was supposed to be posted on the course page also didn't go up until just today. So if you're looking for it, you'll find it on the page for exercise 5. It's the first thing listed here, this exercise 5 tips notebook, and you can then click on that and see what we were highlighting last time, which was basically how to detect if a number is odd or even. And then also how to deal with this issue that has to do with the equation that's used to calculate the glacier flow velocity when you have even exponents, and it does something that kind of looks like what's shown in the plot here for negative values of, I guess it's y in this case, which is the width across the glacier. So, yeah, those are both there, and I wanted to ask you folks, if I give you a few extra days for exercise number 5, what is a reasonable due date? Like, do you want until the end of the week? Because I know Itsenäisyyspäivä is on Wednesday, right? So it's Independence Day, no anything at the university that day. So that kind of makes it a bit weird to like give you 2 extra days, because then that either means like Tuesday and then Thursday, at which point I feel like I should just give you Friday as well, because then you can go to the exercise help session if you still need it. But what do you think? How many of you are like would need an extra day plus for exercise 5? Yeah, a few people. So why don't we just extend it? I won't update the due date on the webpage, but let's extend it to Friday, just because I think if I'm going to give you 2 days, then I'll just give you through till Friday. That way, if you need to get some guidance from Levi in the exercise help session, you have that option. What else about that? Anything? I guess maybe that's covers it. So yeah, apologies about not getting the course page updated sooner. If we turn our focus to this week's lesson, I think everything, let me check, did I make this public yet? Yeah. Everything should be kind of in order here. So this week is kind of the start of the last little piece of the course. So, I mean, I suppose that makes sense from the standpoint that there's only 2 classes left, but more so in the sense that exercises 6 and 7 are closely related to one another, and they're also closely related to the final project for the course. So it's kind of a package deal for the last 2 weeks plus the final project. And so today we'll go through the kind of necessary background material for dealing with exercise number 6 for this week. But I'll also go through a little bit about the final paper or final project to give you an idea of what that includes, because that will ultimately come from some of the results you produce in exercises 6 and 7. Before we do that, are there any other kind of issues or questions you have at this point about anything from last week's exercise that's unclear or other issues. I saw some things on Discord I didn't have a chance to answer in detail about, like people getting weird velocities, but we can discuss that perhaps like individually if we get through all the material for today and have some extra time. Then I can talk people one-on-one about those things. But it sort of seems like there's not too much else on your mind at the moment about exercise 5. So let's jump into our stuff for this week and get on with it. So, as mentioned, in this week, we're going to start our first part of the last kind of 2-week exercise thing. So we'll go through the necessary background stuff and then end up with the final paper. And already on the overview page, you can find some things that'll be useful for you for the final paper. So I'll maybe come back to this after doing the introduction to the final project, but there's some useful stuff here that you'll want to have a look at. But our first stop in terms of content for today is actually going to be here with some lecture slides about low temperature thermochronology. So we talked already back in week number 3, I think, about the kind of general concept of thermochronology, about this dating method where you have a time that records or reflects the time since the rock was at a certain temperature in the interior of the Earth. So that's the kind of idea of a thermochronometer, is that's what you're recording. And we referred to that temperature as the effective closure temperature, and then we talked about in both the lesson and during the exercise this idea that we could use this Dodson's approach to calculate an effective closure temperature based on the condition that as you cool down from high temperatures to low temperatures, the rate of diffusion of your daughter isotope inside the crystal gets slower and slower until eventually it's effectively trapped inside the crystal. And that's when the clock starts ticking for this thermochronology-based dating method. Now, in what we're talking about today, we're focusing on low temperature thermochronology. So we're going to start with a bit of a definition of what do we mean when we talk about low temperature thermochronology. And then I'm going to introduce 3 different types of low temperature thermochronometers, mainly because these will come up in the exercise for, well, both exercises in the next 2 weeks and the final report. So it's good to have a little bit of background because you're going to have data that you're going to be dealing with, and maybe it's useful in some way to have some sense of how these different dating methods are working. Admittedly, this is going to be kind of a short and perhaps like not complete introduction, but it'll at least give you a kind of fundamental sense of how the different methods are working. And we'll focus on helium dating, which we've kind of talked about a little bit already when referring to this Dodson's approach, because it's that's one of the approaches you can use to interpret helium dates. But we'll also talk about fission track dating, which had come up, I think, once earlier in one of the maybe back in like lesson number 3 during the lecture there, and then also argon dating, which is similar in a way to helium dating in that you have a noble gas isotope inside of a crystal lattice. So it's just a bigger isotope, in this case, argon instead of helium. So when we talk about low temperature thermochronology, essentially we're normally talking about thermochronometers where the temperature sensitivity, or the effective closure temperature, is at temperatures below about 300 degrees C. That's not a sort of firm classification, so whether you bump that a little bit higher or a little bit lower varies, I think, from kind of person to person, but generally speaking, we're talking about these systems where you're below temperatures of about 300 degrees C. And if we break it down into like our argon-based systems, these systems based on helium as the daughter isotope or fission track, here's the minerals where we're focusing. So it'd be things like potassium feldspar for the argon system. For helium, it's going to be zircon, titanite, and apatite, although zircon and apatite are certainly the most common in terms of applications. And for fission track, it's the same 3 minerals, more or less. But apatite and zircon, again, are the most popular in terms of fission track dating methods. And you can see here that they've got these effective closure temperatures of anywhere from as low as maybe 75 degrees to something closer to 300 with the titanite system. And for some of them, the range of temperatures can be broader than others. So like potassium feldspar is an interesting one because it's got such a broad range of temperature sensitivities. Now, before we get into the details of those methods, it's also useful to think about why do we care about this? Like, why is it useful? And of course, with a thermochronometer, basically what you record is a time temperature history. So if you have a single age from a single mineral, you have basically a date at which that mineral passed through its effective closure temperature, and then you've collected at the surface, and you know it's taken that long to travel from some depth in the earth up to the surface. So in this little cartoon that's here, for example, if this is a normal fault-bounded mountain range, the uplift of the topography and erosion at the surface will allow you to walk along the surface and collect rock samples, for instance, somewhere here, and they would record the time since they passed through this helium effective closure temperature here nominally is labeled as 60 degrees C, but essentially the part of the pathway that you record in your age is this part from when it passes through the closure temperature up until it reaches the surface. So that's a kind of handy concept in a sense. Well, there's more to it though, because what you can do with that then is you can look at things like how fast would the rate of erosion need to be to get the rocks from this depth up to the surface in the time that your rock sample records. And what you'll see is that there's relationships where you have younger thermochronometer ages in places where you have young topography or actively eroding mountains, and much older ages in places where there's slower rates of erosion or less tectonic activity. And the interest of low temperature thermochronology is to basically be able to study these kind of tectonic and erosional processes over long time scales. So we can go out and look at things like if we went to this river on the little diagram here and measured how much sediment was in the river, we could measure the kind of accumulation and amount of sediment being transported in the river to get some estimate of the rate of erosion. But that's over a time scale of maybe years, probably not even tens of years. Although it depends. If you have a sediment trap that's substantial, you might be able to measure tens of years of sediment accumulating. But that's a very small total amount of time compared to the time it takes to form a landscape like this, which is on the order of millions of years. So that's part of the interest in low temperature thermochronology, is that you can study things that take a long time to form, like mountain ranges that grow over periods of typically tens of millions of years. The low temperature part is appealing because you can see perhaps already here, this is let's say if we take the 60 degrees C as a reference point as our effective closure temperature, this is the depth from the surface down to the 60 degrees C isotherm, and you can see it's affected by the topography. So we have a strong sensitivity to the topography with these low temperature systems because the shape of the Earth's surface will affect the depth to these isotherms, and this effect essentially decreases as you go deeper and deeper or to higher temperatures. So if you go to temperatures of 300 degrees or 350 degrees, you may not see any sign of the topography in the shape of the isotherms, but you see it at low temperatures, which means you can then study those kind of things like how the topography has evolved and changed with these systems. And there's quite a few of them that are here. We already kind of highlighted some of those, so I think we can kind of skip over going through each of these individually and just say that if we consider them in three groups, we'll start with the helium-based systems because they are the ones that have the lowest temperature sensitivity, then go to fission track, and then go to the argon-based systems, essentially going from the lowest temperatures to highest temperatures in terms of the general system sensitivity. So just a couple slides about the dating method itself for helium dating. So as a thermochronometer, this helium dating method, or uranium-thorium helium dating, as it's often referred to, is based on the idea that there are isotopes of uranium and thorium that are radiogenic, and when they decay by alpha decay, they produce a helium atom, essentially, or a nucleus of a helium atom, an alpha particle. It's also true that samarium-147 will produce this, so it's usually a relatively minor constituent, so you will sometimes see this referred to as uranium, thorium, samarium helium dating. But basically, you have these parent isotopes of uranium and thorium. So for uranium, it's 238 and 235. For thorium, it's 232 and then samarium-147 that produce alpha particles. And they do so in the sort of following abundance. So from uranium-238, you get 8 alpha decays. For uranium-235, 7. 6 from thorium-232. And you can see, of course, samarium, in addition to being a relatively minor component, also only produces 1 alpha decay in its chain. But you can see, I guess, I'm not really a sort of super geochemical person, but when uranium-238 starts decaying, it eventually has a daughter product somewhere here that's a lead isotope that's a stable isotope, but along the way, each one of the lines that's kind of diagonally pointing downwards would be an alpha decay where you're producing a helium nucleus. Now, in terms of a chronometer, essentially what you're measuring is the accumulation of that daughter helium inside of the crystal lattice, which will be retained at low temperatures and lost to the surroundings at high temperatures. This is the equation version of what we just said. So we don't necessarily need to go through this, but if you wanted to calculate, for instance, how much helium you would expect to accumulate over a given time period, you can use this age equation to do that. Now, as far as the practicalities go with the dating method, it is a little bit labor intensive. So typically what you're doing is you're dating individual crystals or groups of crystals together, and you have to select them by hand under a microscope. So you crush samples from sort of a bedrock sample into certain size fractions, and then you look through, after doing a bit of separation of the minerals, you look through, for instance, the group of apatites you've isolated for crystals that look like this, that are kind of relatively good looking in the standpoint that they're typically, you want them to be fairly crystal-like in their form, so kind of like prismatic shapes, relatively clear so that you can see through them, and not kind of like these rounded and beat up looking ugly apatites. And this separation process, after doing the kind of bulk separation of the minerals, is done literally by looking at them under a microscope on a slide and picking out crystals, rotating them around, because you have to look for things like inclusions inside the crystals that could contain much higher concentrations of uranium or thorium that will disproportionately produce helium and could bias your ability to interpret the age you get from a given crystal. So it's a slow process. I've never done this myself, and I think I wouldn't have the patience to do it. But it's a hand selection process. There's a lot of little details that go into this. But once you've selected the crystals, you heat them up in a furnace and degas them and measure the helium that comes out. And then you can, in several different ways, I guess you can do it like that. You can also do this with laser ablation with a mass spectrometer, so you can shoot the samples with a laser and blast out a little bit, measure the helium that comes from there, and also get uranium and thorium concentrations that way. But it's done a few different ways. The reason why you want to get these nice prism-shaped crystals is because there is the potential for these alpha particles, when they form, they travel about 20 microns inside the crystal, but they'll also travel 20 plus microns outside the crystal. So they can be ejected for any parent nucleus that's within 20 microns of the edge of the crystal. Basically, you can have helium that gets lost, ejected out of the crystal. So there's a correction that's made based on an assumption that if you're near the edges, you're going to have lost some helium to ejection, and then somewhere in the middle, it should be relatively kind of uniform concentration, and at the other edge, you would be losing some. So we correct for this, but if your crystal's all broken up and not crystal-shaped, then you can't apply that same correction, which means your ability to kind of calculate a reliable age is compromised. So this is yeah, kind of common correction that's done called the alpha ejection correction. And as shown in the example here, it's also possible to have implantation. So you can have neighboring crystals that could produce helium that can get injected into your target crystal as well. So things can be a little bit complicated. So this is a slide from back in lesson 3 about when we introduced thermochronology. It kind of showed these different thermochronometers and how this cooling rate effect applied to them. As you can see from the text that's upside down here, I flipped this diagram upside down to compare it to the next figure that's here. But with the Dodson equation we were using in lesson 3 and in exercise 3, what you see is that as the cooling rate goes up, your effective closure temperature also goes up. So for apatite with helium, it's the daughter isotope, at a cooling rate of 0.1 degrees C per million years, you've got something like a 40 degrees C effective closure temperature, and it's about 80 when you go to a much faster cooling rate of 100 degrees C per million years. So that's the prediction based on Dodson's equation. I decided just to throw in a couple slides at some point to say that this is a nice idea, but things are more complicated in reality. So what happens is that we also have issues with the radiation and the sort of decay of the parent isotope altering the crystal around where the parent isotopes are sitting in the crystal and actually changing the diffusion of helium. So from the alpha decay, when there's an alpha decay, there's a sort of small amount of damage that occurs around the parent isotope where the decay took place. And the damage there results in areas where you can have kind of enhanced trapping of the helium inside the crystal. And so you can end up with these weird behaviors like what's shown in the plot here. So this is for apatite. And this is based on one of these radiation damage models, where here, as the cooling rate is increasing at a given concentration, this is 28 ppm for the parent isotope concentration, you see the effective closure temperature, which is what's on the vertical axis, is going down as the cooling rate is going up, which is just the opposite of what the Dodson model would predict. And the sort of decrease in the closure temperature here is reflecting the fact that this radiation damage is changing the way in which the diffusion of the helium is occurring, and it can change it in sometimes kind of unexpected ways. So here you would normally expect that faster cooling means you're trapping more of the helium, but in this case you're seeing the opposite effect until the cooling rate gets fast enough that it then curves around and you start seeing that trend like what we saw before. And you can see that depending on the amount of the sort of concentration of parent isotope, that effect will be bigger or smaller for apatite. And for zircon, this is the sort of, it's not exactly the same plot, which is why I wanted to sort of put this in big red letters here, that these are not the same type of plot, because here you have cooling rate, here you have alpha dose, which is essentially the amount of radiation damage that the crystal has experienced. But if you look at the closure temperature, this is for zircon helium, it sort of starts with a slow increase as you accumulate alpha damage, and then it rolls over pretty substantially and actually end up with a negative expected closure temperature here. And this behavior is essentially this formation of damage zones where you're trapping helium that occurs in this part where the closure temperature is going up. And then with zircon, because you have a higher concentration of the parent isotopes, you can reach a point where here you've had so much damage to the crystal that the damage zones start to connect, and you actually then can have enhanced loss of helium because you've got sort of like a Swiss cheese zircon. So you have these kind of pathways that helium can easily get out of the crystal. It's on its way to becoming kind of metamict or free of a crystalline structure. And what happens actually in places like Fennoscandia is you have these very weird zero zircon helium ages because there's so much radiation damage because the minerals are old and slowly cooled. So this is something that you can get ages that can vary quite a lot depending on the amount of parent isotope, but some of them are zero even though it's not like it's a zero age from rapid exhumation. It's a zero age because they can't keep any helium in the crystal. So it's a interesting effect. But yeah, this is, I guess, part of the motivation is we explored this a little bit in a paper from last year where we just took some of these radiation damage models and started plotting the different parameters against one another to make these kind of contour plots. And just to show you, for instance, for the apatite helium, here's cooling rate along the horizontal axis, and then this is the apparent isotope concentration on the vertical axis. And as you go across, for instance, at like 40 ppm here, what you see is that as the cooling rate is going up, here's that trend of the closure temperature going down, like what we saw in the previous plot. And then it starts to increase again as the cooling rate is getting faster and faster. It's the same trend you see here where it decreases in the closure temperature and then starts to increase. But things can get even messier for zircon because over here you have the area where you've got so much damage to your crystal, you get these zero ages, and the kind of behavior you get in terms of a expected closure temperature is not really super intuitive. So this is far more complicated than the Dodson model would predict. What we would expect in the Dodson model is that there would be no effect of this parent isotope concentration and only an increase in closure temperature with faster cooling rate. So just wanted to kind of put in a couple slides to show that there's more to this than what we're doing. We'll make a pretty big stride in the last 2 weeks of the exercises to go like all the way to being able to simulate with a thermal model different conditions and predict thermochronometer ages, but there's even more that can be done if you want to worry about radiation damage, which for helium systems at least is pretty important. So yeah, that's kind of the story about the helium-based chronometers. I could say a few things about fission track dating. This won't be, I don't think, part of the data that we're working with for the last exercises, but in case you're curious, it's another dating method. In this case, instead of dating the accumulation of some daughter isotope, you're dating the accumulation of damage trails in the crystal from the spontaneous fission of uranium-238. So this is basically just the nucleus dividing into two roughly equal parts that are charged and push apart from one another and then make damage trails that are on the order of 16 microns in length in apatite or 11 microns in length in zircon. And these are not visible under a normal microscope without doing a bit of sort of etching, so putting the sample into some acid to make the tracks a little bit bigger so you can see them. But this is examples of like images from a microscope where people typically look at individual crystals and count the tracks by hand, like with a little thumb clicker, for example, to see how many tracks you see within a given area. And that density of these damage tracks can tell you how old your sample is. This is something I think it came from maybe already from the 1950s. I think there were some laboratories in the US that were doing things like related to nuclear like radiation exposure and had started doing some dating based on these damage trails. But yeah, you can see here, I mean, there's lots of different ways in which these tracks can intersect the edge of your sample. So normally you've got to cut and polish the sample. And then you've got these sort of exposed parts that you basically dip into some nasty acid at a high temperature that enlarges the tracks. So the ones that hit the surface of the sample will get enlarged naturally, but then there can also be like things like cleavage or another track that intersects one that can be a pathway for things to get into the interior of the crystal and hit a track like this. And these are the ones that you normally want to count, these kind of confined tracks, because if you have one that hits the surface somewhere, you can't measure its length because part of it is not there. So typically what you're measuring are these confined tracks that are inside the crystal, and those then allow you to measure the length of a track which can be useful as well. But as far as the dating method goes, the kind of general concept, like any thermochronometer, is that in this case, the damage repairs itself in the crystal at high temperature. So, with our helium's being diffused out of the crystal at high temperature here, these damage pathways are repaired within the crystal structure. So they go away at higher temperature and are thought to be relatively stable at low temperature, although that's not entirely agreed upon that these are stable over like hundreds of millions of years. There's some question about whether that's reality. But that's just a couple slides on fission track dating, just for the sake of completeness. And if you want more information, of course, you can find some things in the references, for instance, here. Then lastly, about argon dating, and then we'll move on to some other things. But essentially, the argon dating method is based on this case on the decay of potassium-40 to radiogenic argon-40. And so obviously, as you know, potassium is one of the most abundant rock-forming or elements in rock-forming minerals, especially in the crust, so good target in that sense. And argon-argon dating is typically used on things like white micas or biotite, potassium feldspar, and amphiboles. So you can date a lot of different minerals with the argon-argon dating method. So that's what makes it appealing. The approach is a little bit more complicated. I'm not going to go into this in detail, but normally there's an irradiation that has to be done to the sample, and then you're measuring a ratio of argon isotopes to get your age. And that's something that can be done by degassing the entire crystal and measuring the amount of the two argon isotopes, or you could do step heating, which is an interesting alternative that can give you a little bit more information. And again, the details of the dating method here are not so important, but you can find the slides there. For instance, if you're working on your final project and you want to look up something about argon-argon, this is a good place to start. But the idea with the step heating is that if you have some rock that's been rapidly cooled, typically what you'll see is that the argon concentration of argon-40 that's been produced naturally from potassium-40 will be fairly constant across from one rim of your mineral to the other rim. And that constant concentration is an indication of basically rapid cooling, like you would expect, for instance, from some kind of volcanic eruption. Those minerals that form in that case are typically cooled very quickly and would preserve this kind of constant argon profile, compared to something like slow cooling, where you can see here that the rims, you have almost no argon. In the center of the crystal, you still have some. And when you're measuring these kind of ratios, what you're going to see is that exact thing in the pattern, that the argon-39 would be from the irradiation you've done. That's going to be constant in both cases, but then the natural argon-40 would be varying. And the step heating is basically where you kind of take these samples inside a furnace and just heat them for different intervals of time at a given temperature and see how much argon is released as you sequentially heat up. Typically with the idea being that you're going to heat and release argon from the edges of the crystals and move toward the center of the crystal as it gets hotter and hotter. So in the constant spreading case, this is the amount of argon that's measured. It's constant across the sort of full time you're doing the heating. But then here you can see that you've got little amount of argon released at the beginning of your step heating experiment, and more as you go on with time, as you're basically kind of moving further into the interior of the crystal with where the argon is being sourced. So this is nice in the sense that this can actually tell you something about the distribution of argon inside the crystal, which relates to its cooling history. You don't know up front whether it's rapid. Well, maybe you know if it's rapid or slow cooling if it's a volcanic eruption, but oftentimes you don't necessarily know whether you have rapid or slow cooling until you start measuring things. So that's why the step heating can be useful. But yeah, with argon dating, an ideal situation, if you've got a constant concentration, would be like this line A, where you heat it up and you get a constant amount of argon out each one of the steps that you have in there that indicates rapid cooling. Okay, B would be something where the amount of argon being released initially is low and it increases And that would then, for instance, tell you something about slow cooling, potentially. But then there's sometimes when you get something like C, where you get a lot of argon released and then it actually decreases as you go toward the center of the crystal. And this is kind of not expected and not really good. This is what's called excess argon, and this is why certain minerals are not so popular for dating with argon-argon, because some of them have a tendency to have excess argon at the rims for some reason, whether that's coming into the crystal from outside, whether it's zoning or whether it's something else. It's not entirely clear, but this, at least with biotite, for example, it's common that you have this excess argon, and it's thought to be something about argon being absorbed from the surroundings into the edges of the crystal, which means as a dating method, it's not so useful because you lose this ability to kind of use the edge of the crystal as something that can tell you about the rapid cooling or slow cooling. So you'll have some argon ages you're going to deal with in the two exercises. Maybe not today. I guess it's exercise 7 in the final project. You'll have some argon ages. Again, if you're curious about the dating method itself, then you can maybe refer back to the slides to see that. But you'll have data that you'll have apatite and zircon helium data, and then argon in, I think, argon in muscovites for the data set you're dealing with the last exercise 7 in the final project. Are there any questions at this point? I think what I'm kind of sharing is largely just background information that you can use to understand a little bit more about what these ages mean when you deal with them in the exercise 7 and the final project. But are there any general questions? Okay. So, I think we can skip the little recap and go to our other set of slides before we look at this week's exercise. And this is kind of the overview of exercises 6 and 7, which are both about this kind of quantitative thermochronology as a general theme. So for exercise 6 and 7, we're going to be dealing with data from a paper from the Himalaya of Bhutan. It's a very nice place. This is not my photo, but it's obviously quite scenic place to do field work, and the margin of the kind of largest continent-continent collision we have active today. So as you might imagine, this is an area that's rapidly being eroded away and uplifted by active faults and things like that. We're going to be working with data from a transect in western Bhutan. So here we are in terms of our map view. There's India and the Himalaya. There's the sort of frontal thrust of the Himalaya running along here. And this is our study area, in this case, in western Bhutan. And all of the little colored dots in this map, in this western transect, are places where there was rock sample collected and dating that was done. And we're going to be using apatite and zircon helium ages, so the green and the pink points off of or from out of this data set. We're not going to deal with the fission track data because Dodson's approach doesn't really suit working with fission track data that well. But this is our study area in a sense, and this is paper from 2014. And you'll have the reference information for that if you want to look up and read more information there. So here's a plot of the age data. So the vertical axis here is age, and this is latitude. So we're kind of going from south to north in this transect. And you can see the age pattern in here is a bit complicated. If you look at just one age system, so for instance, the pink dots here, if I'm not mistaken, those should be our zircon helium ages. And you can see that they're sort of young in the very southern edge, and then they get a little bit older, and then there's a sort of continual decrease in ages as you go further north, and then you get a little bit older ages again further north. And most of the chronometers show somewhat of a similar pattern, that the ages are kind of very young in the south, get a bit older, decrease toward the kind of central part of this transect, and then get a little bit older as you go north from there. in the absence of any other tools here, interpreting this age data set would not be something that's so easy to do, because ultimately what we want to do is connect these ages to something like rates of erosion or rates of fault motion or things like this, like some kind of geological process. And that's not necessarily an easy thing to do directly from the ages themselves. So, well, yeah, just as a reminder before we go to our calculation of an exhumation rate, in most mountainous places, especially where you have two continents colliding or kind of convergent tectonics, most of the reason that the rocks are exhumed and brought from depth to the surface is due to erosion. So you have things like rivers and glaciers that are eroding the surface, and landslides and other processes that are basically removing material at the surface and exposing rock beneath it, and active over long periods of time. You can get rocks from tens of kilometers depth up to the surface. And of course, that's the process. It's same thing that's going to be active where we're working with our little toy data set. Going back to the question of if we want to go from some age we have to a rate of some process, how might we do that? So imagine you have some age and you want to know how fast did this rock come to the surface? What information would you need to be able to do that? Yeah, right? So in order to do this, we need to have some depth at which we can say, okay, our closure temperature was this depth below the surface. Once we have that, we then have a distance, which is basically the depth up to the surface, and an age. And if you divide that distance by the age, that is the rate at which the rock came up to the surface. So the simple way to do that, if you don't want to actually try to figure out with a more sophisticated model how deep was your closure temperature, is to assume a kind of typical geothermal gradient. So if we say it's 20 degrees C per kilometer, if we have a closure temperature of 75 degrees C, we can figure out from this that we would have to go whatever 3.75 kilometers or 3.5 kilometers down to hit 75 degrees C. But yeah, in essence, we can figure out how deep is that closure temperature and divide that by divide the depth by the age and get a rate. So here we have our 3.75 degrees C, which is basically just if we assume 0 at the surface, and 20 degrees C is how much the temperature increases with each kilometer we go down. We've got to go to 3.75 kilometers depth before we hit 75 degrees C. That's our distance our rock sample has to travel. If we have an age, for instance, of 12.3 million years, then our exhumation rate will simply be that 3.75 kilometers divided by 12.3, or about 0.3 kilometers per million years, which is the same as the sort of 0.3 kilometers per 0.3 millimeters rather per year as an exhumation rate. So that's one way you can do it, is basically just to assume a geothermal gradient, figure out what depth your temperature's at, and then divide that depth by the age. That's a perfectly suitable way to do that. But there are some problems with that because it ignores a lot of things that are important for bending the geotherm. So things like heat production and advection both will cause curvature in your geotherm with depth. Then there's also things like topography that can also be an additional piece. So a better approach is to actually use a thermal model to estimate the depth to the closure temperature and calculate the exhumation rate that way. And that's what we're going to do in the last two exercises. So we already have a code that does something like this. This version, this is a kind of steady state calculation, but you guys have this code you made in exercise number 4, I think, that allowed you to do temperature calculation in sort of transient temperature calculation. That was our advection diffusion equation exercise. So you can essentially calculate what you think the temperature would be as a function of depth in a geotherm, like what's shown in the plot here. And advection, of course, as you might have seen in the exercise, higher rates of advection tend to produce higher geothermal gradients. And so advection is going to be something that's important for us, especially in a rapidly eroding mountain area like in the Himalaya. So we need to have an equation that includes that. Well, we already have one from exercise 4, so we can take advantage. But in order to use our code from exercise 4, which calculates temperature, we have to be able to record a kind of temperature history of our rock as it moves from depth up to the surface. So we have a code to get us a temperature, this whatever it was called, transient temp, whatever that function was called in exercise 4, I don't remember the name. But we have that'll allow us to calculate what the temperature is at any given time in our model. But we need to somehow record a temperature history of a rock as it travels from depth to the surface, because we need to know when does it pass through the closure temperature. When does it cool below that closure temperature on its way up to the surface? We can assume that we've collected the rock sample we're going to be dating at 0 MA at the surface today. And our way to get a cooling history is that we can basically take our advection velocity, and if we assume that erosion balances the rate at which rock is moving up to the surface, we can essentially use a little trick here to calculate things like this. So every time, for instance, if we start out with our rock sample at some depth here, after some period of time, it will have moved to a shallower depth along this temperature history that looks like this. So imagine it started at 20 kilometers depth, just arbitrarily. We can move up to a shallower depth by whatever our time step is multiplied by the advection velocity. That gives you some distance. And then you can say, okay, well, what's the temperature at this point? And then move up a little bit more. What's the temperature here? What's the temperature here? And so on. And like that, you can produce a temperature history. So as the rock goes from depth to the surface, you can record what its temperature is, and then you can use that to calculate your thermochronometer ages, and then compare those to what has been provided for you in the data set that you're going to be working with. So things are a little bit more complicated than what's shown in the diagram here, but you have tools to do this geotherm calculation part already. That's not a problem. You've got a code that'll do that for you. You will need to write code in this week's exercise to do this thing about like tracking the particle depth of your rock from depth up to the surface, but that's not too terribly difficult to do, and we'll go through that in just a moment. But once you have the temperature history, it's easy to get a thermochronometer age from there. So in the last two exercises, you're basically going to have something where you make this time depth history, which is essentially just how deep was your rock at different times in its history. Use that to figure out what was the temperature at each point as you cooled from depth up to the surface, and then use that temperature history to get your closure temperature. And then once you have your closure temperature, you can figure out what depth you pass through the closure temperature, and then you know your age at that point. And what you'll do in next week's exercise is then compare that to the data set that's been provided for you using this goodness of fit statistic, this chi-squared statistic we dealt with back in week number 2. So you'll be able to compare like what is my prediction compared to the observed ages, and that will tell you how well is your model doing in terms of predicting an age, that how does it compare to what's been measured for the rock samples in this Western Bhutan study area. And then you can iterate on the steps 1 through 5 to try to get your model to do a better job of predicting the observed ages. I think that's the end of those slides, but just go back here for a second, maybe to this diagram, just to reiterate, essentially what we're doing is we're going to have these ages like this, the pink points here, and we're saying, let's figure out what the rate of rock exhumation would be that would produce these ages. And we're going to use a little bit of new code, but also things you've already written earlier in the course to be able to do this. I've got a feeling you guys are confused. Maybe it's just my perception, but are there some things I could perhaps clarify about the kind of overall idea here for exercise 6 and 7? All right, maybe let's do it like this. By show of hands, how many of you feel like you have a pretty good idea of what's going on for exercises 6 and 7? Okay, there's like 3-ish reluctant, halfway raised hands. That's fine. I mean, to be totally honest, it's not necessarily, I mean, the good thing about this is that you have 2 exercises and a final project that are all related to the same thing, and it might take a little bit of time for you to kind of understand fully what's going on. But in essence, our idea is to say, like, we want to use this thermochronology approach to measure long-term rates of rock exhumation. We have these ages at the surface that say, okay, for instance, for these pink points here, it's been 8 million years since the rock was at this closure temperature, and I think this is for zircon helium for the pink color. So let's say 200-ish degrees 8 million years ago. The kind of task that you're given in this case is to say, okay, now use a thermal model to figure out what depth was 200 degrees at, and then with the thermal model, what you do is you're going to run it forward, and it's going to predict for some advection velocity that you provide, it'll tell you what the age is for that advection velocity. And you want to kind of then change that advection velocity until you start to get ages around 8 million years, for example, for your zircon helium. That's not exactly, I mean, that's kind of simplifying things a bit, but if you imagine, that's the target idea, is to kind of play with the model, change the advection velocity until you get ages around the ages that the this data set records. So you should see that if you make the advection velocity really slow, you get old ages that are too old, they don't fit the age data. If you make it really fast, they get too young and they don't fit the age data. So it's kind of a Goldilocks thing. You're going to turn the knob in the model until you get a good-ish match to the age data. The reality here is that there's a lot of other factors that affect the ages here, like structural position and elevation and lots of other things that make this more complicated, but we can still have some fun with our code and explore a bit of this age data set. At this point, why don't we take 5 minutes, and then we can come back and have a look at the exercise number 6, and then also have a look at the final paper info. So let's come back. Why don't we say 20 after 3? So 7 minutes from now.